Chapter 2, the Rust Programming Language, Programming a Guessing Game. Let's jump into Rust by working through a hands-on project together. This chapter introduces you to a few common Rust concepts by showing you how to use them in a real program. You'll learn about let, match, methods, and associated functions using external crates and more. The following chapters will explore these ideas in more detail. In this chapter, you'll practice the fundamentals. We'll implement a classic beginner programming program, a guessing game. Here's how it works. The program will generate a random integer between 1 and 100, and it will then prompt the player to enter a guess. After the guess is entered, the program will indicate whether the guess is too low or too high. If the guess is correct, the game will print a congratulatory message and exit. Setting up a new project. To set up a new project, go to the projects directory you created in Chapter 1 and make a project using Cargo like so. The first command, cargo new, takes the name of the project, guessing_game, as the first argument. The second command changes the new project's directory. Look at the generated Cargo.lock file. File name Cargo.lock. If the author information in the cargo obtained from your environment is not correct, fix that in the file and save it again. As you saw in Chapter 1, Cargo New generates a Hello World program for you. Check out the src main.rs file. Now let's compile this Hello World program and run it in the same setup using the cargo run command. The run command comes in handy when you need to rapidly iterate on the program, as we'll do in this game, quickly testing each iteration before moving on to the next one. Reopen the src/main.rs file. You'll be writing all the code in this file. Processing a guess. The first part of the guessing game program, we will ask for user input. Process that input and check that the input is in the expected form. To start, we'll allow the player to input a guess. Enter the code listing 2-1 into your src main.rs file. So they want you to put this code in the file. This code contains a lot of information, so let's go over it line by line. To obtain user input and then to print the results as output, we need to bring the IO input-output library into scope. The IO library comes from standard library, which is known as std. Okay, by default, Rust brings only a few types into the scope of every program in the prelude. If a type you want to use isn't in the prelude, you have to bring that type into scope explicitly with the use statement. Using the std : or whatever that's called library provides you with a number of useful features, including the ability to accept user input. As you saw in Chapter 1, the main function is the entry point into the program. The fn syntax declares a new function. The parentheses indicate that there are no perimeters, and the curly brackets start the body of the function. As you also learned in Chapter 1, println is a macro that prints a string to the screen. This code is printing a prompt stating what the game is and requesting input from the user. storing values with variables. Next, we'll create a place to store the user input like this. Now the program is getting interesting. There's a lot going on in this little line. Notice that this is a let statement, which is used to create a variable. Here's another example. This line creates a new variable named foo, and it binds to the value of the bar variable. In Rust, variables are immutable by default. We'll be focusing this concept in detail in the variables and mutability section in chapter 3. The following example shows how to use mut before the variable name to make the variable mutable. Let foo equal 5. Let foo bar equal 5. Okay, note that the / syntax starts, where's that backslash? I always get those confused. Syntax starts a comment that continues until the end of the line. Rust ignores everything in the comments, which are discussed in more detail in this chapter. In chapter 3. Let's return to the guessing game program. Now you know that the let, mut, guess, and I'm just going to go mut, M-U-T. Guess will introduce a mutable variable named guess. On the other side of the equal sign is the value of guess is bound to, which is the result of calling string, new, I don't know what to call them. Maybe I should look that up quick. Colon, I'm not sure. Anyway, a function that returns a new instance of the string. String is a string type provided by the standard library that is a growable UTF-8 encoded bit of text. Let's see, I'll go ahead and look that up. I'm sure my readers already know what that is, but colon, okay. Well, string : new, a function that returns a new instance of the string. String is a string type provided by the standard library that is growable, UTF-8 encoded bit of text. The : syntax in the : new line indicates that the new is an associated function of the string type. An associated function is implemented on a type. In this case, string, rather than on a particular instance of a string. Some language call this a static method. This new function creates a new empty string. You'll find a new function on many types because it's a common name for a function that makes a new value of some kind. To summarize, the let mut guess equals string : new. Well, what are brackets? Not curly brackets. Line has created a mutable variable that is currently bound to a new empty instance of a string. Phew. Parentheses. Line has created a mutable variable currently bound to a new empty instance of a new string. Phew. Recall that we included the input/output functionality from the standard library with the use std : IO. Let's see, okay, and then I got the code. Let's see, if we hadn't put the use std : IO line at the beginning of the program, we could have written this function as std : IO : st stdin, the stdin function returns an instance of std io stdin, which is a type that represents a handle to the standard input for your terminal. The next part of the code, read_line colon, or what does that call again? Parentheses, at, and mute space guess calls the read_line method on standard input handle to get the input from the user. We're also passing one argument to the read_line colon and mute guess. The job of read_line is to take whatever user types into standard input and place that into a string, so it takes that string as an argument. The string argument needs to be mutable so that the method can change the string's content by adding the user input. The AND indicates that this argument is a reference, which gives you a way to let multiple parts of your code access one piece of data without needing to copy the data into memory multiple times. References are a complex feature, and one of Rust's major advantages is how safe and easy it is to use references. You don't need to know a lot about those details to finish this program. For now, all you need to know is that, like variables, references are immutable by default. Hence, you need to write and mute space guess rather than and guess to make it mutable. Chapter 4 will explain references more thoroughly. Handling potential failure with the result type. We're not quite done with this line of code, although we discussed so far as a single line of text. It's only the first part of the single logic line of code. The second part is method. When you call a method with a .foo syntax, it's often wise to introduce a new line and other white space to help break up the lines. We could have written this code as, and here they have the code. However, one line is difficult to read, so it's best to divide it, 2 lines for 2 method calls. Now let's discuss what this line does. As mentioned earlier, read_line puts what the user types into the string we're passing it, but also returns a value. In the case an IO, glad I kept this up here, colon result. Rust has a number of types named result in its standard library, a generic result as well as specific versions for submodules such as IO: result. The result types are enumerations, often referred to as enums. An enumeration is a type that that can have a fixed set of values, and those values are often called the enums variant. Chapter 6 will cover enums in more detail. For result, the variants are OK or error. The OK variant indicates the operation was successful inside OK and is the successfully generated value. The error variant means the operation failed, and the error contains information about how or why the operation failed. The purpose of these result types is to encode error handling information. Values of the result type, like values of any type, have methods defined on them. An instance of an IO result has an expect method that you can call. If this instance of IO result is an error value, expect will cause the program to crash and display the message that you passed as an argument to expect. If the read_line method returns an error, it would likely be the result of an error coming from the underlying operating system. If this instance of an IO result is an OK value, expect will take the return value that OK is holding and return just the value to you so you can use it. In this case, that value is the number of bytes in what the user entered into standard input. If you don't call expect, the program will compile, but you will get a warning. Rust warns that you haven't used the result value returned from read_line, indicating that the program hasn't handled a possible error. The right way to suppress the warnings is to actually write error handling. But because you just want the program to crash, you just want to crash this program, when a problem occurs, you can use expect. You'll learn about recovering from errors in Chapter 9. Printing values with println placeholders. Aside from the closing curly brackets, there are only one more line to discuss in code added so far, which is the following. And there you have the code. This line prints the string we saved to the user's input in. Let's see, this line prints the string we saved the user's input in. The set of curly brackets is the placeholder. Think of the curly brackets as little crab pinchers that hold a value in place. You can print more than one value using the curly brackets. The first set of curly brackets hold the first value listed under the format string. The second hold the second value, and so on. Printing multiple values in one call to print line would look like this. There's your print line, X, and then anything that's in here is going to be 5, and Y, anything in here is going to be 10. And you call this with the X here and this with the Y here. This code would print X equals 5 and Y equals 10. So text X equals 5 and Y equals 10. Testing the first part. Let's test the first part of the guessing game. Run it using Cargo run. I've got the code here. At this point, the first part of the game is done. We're getting input from the keyboard and then printing it. Generating a secret number. Next, we need to generate a secret number that the user will try to guess. The secret number should be different every time so that the guessing game is fun to play more than once. Let's use a random number between 1 and 100 so that the game isn't too difficult. Rust doesn't yet include random number functionality in its standard library. However, the Rust team does provide a rand crate. Using a crate to get more functionality. Remember that a crate is a collection of Rust source code files. The project we've been building is a binary crate, which is executable. The rand crate is a library crate which contains code intended to be used in other programs. Cargo's use of external crates is where it really shines. Before we can write code that uses rand, we need to modify the Cargo.toml file to include the rand crate as a dependency. Open up that file now and add the following line to the bottom beneath the dependencies section header that Cargo created for you. File name Cargo.toml. And you should see a line with dependencies, and you add rand equals, and Let's see, in the cargo toml, everything that follows the header is part of the section that continues until another section starts. The dependencies section is where you tell Cargo which external crates your project depends on and which version of those crates are required. In this case, we'll specify the RAND crate with the semantic version specifier 0.5.5. Cargo understands semantic versioning, sometimes called semver, which is a standard for writing version numbers. The number 0.5.5 is actually shorthand for, well, you get it, which means that any version that has a public API compatible with version 0.5.5. Let's see, now without changing any code, let's build the project as shown in listing 2-2. And I give an example. Listing 2-2, the output from running cargo build after adding the RAND crate as a dependency. Okay, you may see different version numbers, but they will all be compatible with the code thanks to semver. And the lines may be in a different order. Now that we have an external dependency, Cargo fetches the latest versions of everything from the registry, which is a copy of the data from Crates.io. Crates.io is where people in the Rust ecosystem post their open source Rust projects for others to use. After updating the registry, Cargo checks the dependencies section and downloads any crates you don't have yet. In this case, although we listed RAND as a dependency, Cargo also grabbed libc and rand_core because RAND depends on those to work. After downloading the crates, Rust compiles them and then compiles the project with the dependencies available. If you immediately run the cargo build again without making any changes, you won't get any output aside from the finished line. Cargo knows it has already downloaded and compiled the dependencies, and you haven't changed anything about them in your cargo toml file. Cargo also knows that you haven't changed anything about your code, so it doesn't recompile that either. With nothing to do, it simply exits. If you open up the src/main.rs file, make a trivial change and then save it and build it again, you will only see 2 lines of output. Okay. These lines show Cargo only updates the build with your tiny change to the src/main.rs file. Your dependencies haven't changed, so Cargo knows it can reuse what it already has downloaded and compile it for those. It just builds your part of the code, ensuring reproducible builds with the Cargo.lock file. Cargo has a mechanism that ensures you can rebuild the same artifact every time you or anyone else builds your code. Cargo will use only the versions of the dependencies you specify until indicated otherwise. For example, what happens if next week version 0.5.6 of the RAND crate comes out and contains an important bug fix, but also contains a regression that will break your code? The answer to this problem is the Cargo.lock file, which was created at the first time you ran cargo build and is now in your guessing_game directory. When you build a project for the first time, Cargo figures out all the versions of the dependencies that fit the criteria and then writes them to the Cargo.lock file. When you build your project in the future, Cargo will see the Cargo.lock file exists and use the versions specified there rather than doing all the work to figuring out versions again. This lets you have a reproducible build automatically. In other words, your project will remain at 0.5.5 until you explicitly upgrade thanks to the Cargo.lock file. Updating a crate to get a new version. When you do want to upgrade a crate, Cargo provides another command, update, which will ignore the Cargo.lock file and figure out all the latest versions that fit your specifications in Cargo.toml. If that works, Cargo will write those versions to the Cargo.lock file. By default, Cargo will only look for versions greater than 0.5.5 and less than 0.6.0. If the RAN crates has released two new versions, 0.5.6 and 0.6.0, you will see the following RAN Cargo update. At this point, you would also notice that the change in the Cargo.lock, noting that the version of the RAN crate you are now using is 0.5.6. If you wanted to use RAN version 0.6.0 or any other version in the 0.6.x series, you will have to update the Cargo.toml file to look like this instead. The next time you run Cargo build, Cargo will update the registry of crates available, reevaluate your RAND requirements according to the new version you have specified. There's a lot more to say about Cargo and its ecosystem, which we'll discuss in Chapter 14, but for now, that's all you need to know. Cargo makes it very easy to reuse libraries, so Rusticians are able to write smaller projects that are assembled from a number of packages. Generating a random number. Now that you added the RAND crate to Cargo.toml, let's start using RAND. The next step is to update src/main.rs as shown in listing 2-3. Listing 2-3, adding code to generate a random number. First we add a use line. Use rand : RNG. The RNG trait defines methods that random number generators implement, and this trait must be in scope for us to use those methods. Chapter 10 covers traits in detail. Next, we're adding two lines in the middle. The rand : thread _RNG function will give us the particular random number generator that we are going to use, one that is local to the current thread, of execution and seeded by the operating system. Then we will call gen_range method on the random number generator. This method is defined by the RNG trait that we brought into scope with the use rand : RNG statement. The generate_range method takes two numbers as arguments and generates a random number between them. It's inclusive on the lower bound, but exclusive on the upper bound, so we need to specify 1 and 101 to request a number between 1 and 100. Note: you won't just know which traits to use and which methods and functions to call from a crate. Instructions for using a crate are in each creates documentation. Another neat feature of Cargo is that you can run the Cargo.lock --open command, which will build documentation provided by all of your dependencies locally and open it in your browser. If you are interested in other functionalities in the rand crate for example, run Cargo.lock open and click rand in the sidebar on the left. The second line that we added to the middle of the code prints the secret number. This is useful while we're developing the program to be able to test it, but we'll delete it from the final version. It's not much of a game if the program prints the answer as soon as it starts. Try running the program a few times. You should get different random numbers, and they should all be numbers between 1 and 100. Great job. Comparing the guess to the secret number. Now that we've user input and a random number, we can compare them. That step is shown in listing 2-4. Note that some code won't compile quite yet, as we will explain. Listing 2-4 handling the possible return values of comparing two numbers. The first new bit here is another use statement, bringing a call type std : mcmp : ordering into scope from the standard library. Like result ordering is another enum, but the variant of ordering are less, greater, and equal. These are the three outcomes that are possible when you compare two values. When we add 5 new lines at the bottom that use the ordering type, the CMP method compares two values and can be called on anything that can be compared. It takes a reference to whatever you want to compare with. Here are comparing the guess to the secret number. Then it returns a variant of the ordering enum we brought into scope with the use statement. We used a match expression to decide what to do next based on which variant of ordering was returned with the call to CMP with the values and guess and secret _number. A match expression is made up of arms. An arm consists of a pattern and the code that should be run if the given value to the beginning of the match expression fits that arm's pattern. Rust takes the value given to the match and looks through each arm's pattern in turn. The match, construct, and patterns are powerful features in Rust that let you express a variety of situations your code might encounter and make sure that you handle them all. These features will be covered in detail in Chapter 6 and Chapter 18 respectively. Let's walk through an example of what would happen with the match expression used here. Say that the user guessed 50 and from the random generated secret number this time is 38. When the code compares 50 to 38, the CMP method will return ordering greater. Because 50 is greater than 38, the match expression gets the ordering greater value and starts checking each arm's pattern. Let's see, it looks at the first arm's pattern, ordering less, and sees that the value of ordering greater does not match ordering less, so it ignores the code in the arm and moves on to the next arm. The next arm's pattern, ordering greater, does match ordering greater. The associated code in the arm will execute and print too big to the screen. The match expression ends because it has no need to look at the arm's let's see, arm in this scenario. However, the code in listing 2-4 won't compile yet. Let's try it. Let's see, the core of the error states that there are mismatched types. Rust has a strong static type system. However, it also has type interference. When we wrote let mut guess equal string new, Rust was able to infer that guess should be a string and didn't make us write the type. The secret number, on the other hand, is a number type. A few number types can have a value between 1 and 100. I32, a 32-bit number, U32, an unassigned 32-bit number, I64, a 64-bit number, as well as others. Rust defaults to an I32, which is the type of secret number unless you add type information elsewhere that would cause Rust to enter a different numerical type. The reason for the error is Rust cannot compare a string to a number type. Ultimately, we want to convert the string the program reads as input into a real number type so we can compare it numerically to the secret number. We can do that by adding the following two lines to the main function body. The two new lines are: we create a variable named guess, but wait, doesn't the program already have a variable named guess? It does, but Rust allows us to shadow the previous value of guess with a new one. This feature is often used in situations in which you want to convert a value from one type to another type. Shadowing lets us reuse the guess variable named rather than forcing us to create two unique variables such as guess underscore str and guess, for example. Chapter 3 covers shadowing in more detail. We bind guess to the expression guess.trim. Let's see, the guess in the expression refers to the original guess that was a string with the input in it. The trim method on string instance will eliminate any white space at the beginning and the end. Although U32 can contain only numerical characters, the user input must enter to satisfied read underscore line. When the user passes enter, a new line character is added to the string. For example, if the user types 5 and then presses enter, guess looks at this 5 \n. The \n represents new line, the result of pressing enter. The trim method eliminates the \n, resulting in just 5. The parse method on strings parses the string into some kind of number. Because the method can parse a variety of number types, we need to tell Rust the exact type number type we want by using let guess U32. Excuse me. The colon after guess tells Rust we'll note the variable's type. Rust has a few built-in number types. U32 seen here is an unassigned 32-bit integer. It's a good default choice for a small positive number. You'll learn about number types in Chapter 3. Additionally, U32 annotation in this example program and the comparison with secret underscore number means that Rust will infer that the secret number should be U32 as well. So now the comparison will be between two values of the same type. The call to parse could easily cause an error. For example, the string contained, there would be no way to convert that to a number because it might fail. The parse method returns a result type, such as a read underscore line method does, discussed earlier in handling potential failure with the result type. We'll treat this result as the same as using expect method if parsed returns an error. Result variant because it couldn't create a number from the string. The expect call will crash the game and print the message we gave it. If parse can successfully convert the string to a number, it will return the OK variant of result, and expect will return the number that we want from the OK value. Let's run the program now. Nice, even though spaces were added before the guess, program still figured out the user guessed 76. Run the program a few times to verify the different behavior with different kinds of input. Guess the number correctly. Guess the number that is too high and guess a number that is too low. We have most of the game working now, but the user can only let's see. But the user can make only one guess. Let's change that by adding a loop, allowing multiple guesses with looping. The loop keyword eliminates the infinite loop. We'll add, that now to give users more chances to guessing the number. As you can see, we've moved everything into a loop from the guess input prompt onwards. Be sure to indent the lines inside the loop, another 4 space each, and run the program again. Notice that there is a new problem because the program is doing exactly what we told it to do for another guess forever. It doesn't seem like the user can quit. The user could always interrupt the program by using the keyboard shortcut Control-C. But there's another way to escape this insatiable monster. As it's mentioned in the parse discussion in comparing the guess to a secret number, if the user enters a non-number answer, the program will crash. The user can take advantage of that in order to quit, as shown here. Typing quit actually quits the game, but so will any other non-number input. However, this is suboptimal to say the least. We want the game to automatically stop when the correct number is guessed, quitting after a correct guess. Let's program the game to quit when the user wins by adding a break statement. Adding the break line after you win makes the program exit the loop when the user guesses the secret number correctly. Exiting the loop also means exiting the program because the loop is the last part of main. Handling invalid input. To further refine the game's behavior, rather than crashing the program upon the user's input, a non-number, let's make the game ignore a non-number so that the user can continue guessing. We can do that by altering the line where guess is converted from a string to a U32 as shown in listing 2-5. Listing 2-5, ignoring a non-number guess and asking for another guess instead of crashing the program. Switching from an expect call to a match expression is how you generally move from crashing an error to handling the error. Remember that parse returns a result type, and result is an enum that has the variance OK or error. We are using the match expression here as we did with ordering the result of the CMP method. If parse is able to successfully turn the string into a number, it will return an OK value that contains the resulting number. That OK value will match the arm's first pattern, and the match expression will just return the num value that parse produced and put inside the OK value. The number will end up right where we want it in the new guess variable we're creating. If parse is not able to turn the string into a number, it will return an error value that contains more information about the error. The error value does not match the OK nums pattern in the first match arm, but does match the error pattern in the second arm. The underscore is a catch-all value. In this example, we're saying that we want to match all error values no matter what information they may have inside them. So the program will execute the arm's second code. Continue, which tells the program to go to the next iteration of the loop and ask for another guess. So effectively, the program ignores all errors that parse might encounter. Now everything in the program should work as expected. Let's try it. Awesome. With one tiny final tweak, we will finish the guessing game. Recall that the program is still printing the secret number. That worked well for testing, but it ruins the game. Let's delete the print line that outputs the secret number. Listing 2-6 shows the final code. Listening 2-6 complete the guessing game code. Summary: at this point you've successfully built the guessing game. Congratulations. This project was a hands-on way to introduce you to many new Rust concepts: let, match, methods, associated functions, and use of external crates, and more. In the next few chapters, you'll learn about these concepts in more detail. Chapter 3 covers concepts that most programming languages have, such as variables, data types, and functions, and show how to use them in Rust. Chapter 4 explores ownership, a feature that makes Rust different from other languages. Chapter 5 discusses structs and methods, and Chapter 6 explains how enums work. That is the ending of Chapter 2. Okay, so we'll see you hopefully back at Chapter 3.